Hello, my name is Barry Tillman, and I'll be presenting a talk entitled Predicting Shelling Rate of Peanut Genotypes from the Uniform Peanut Performance Test. My co-author in this is Dana Burgos. First of all, what is shelling rate and why is it important? Well, shelling rate is the farmer stock mass shelled per unit time. In this case, it was measured in grams per minute. It's from a rotary sheller. It's important to realize that this rotary sheller is different than the type of sheller that breeders use and is used in the commercial trade that are reciprocating shellers. And those reciprocating shellers are the ones that we use in our grading programs and grading processes to determine the value of the peanuts. But commercially, peanuts are shelled with a rotary sheller. And that commercial shelling efficiency is important for variety acceptance. And some cultivars have failed due to slow shelling characteristics. So our goal is to predict shelling rate from the rotary sheller using information gathered from the reciprocating sheller. So this is just an example of what a rotary sheller and a reciprocating sheller look like. You see here that the rotary sheller, it's a miniature version of a commercial shelling machine, has rotating bars on a shaft that will break the shells of the peanut and allow the peanuts to fall through a grate here at the bottom. And you see there are sheller bars, as we see here, and there is a sheller screen or sheller grate at the bottom. And that's the same case with the reciprocating sheller, except the motion of the shelling process is back and forth like this, not circular. And so the sheller bars move along a similar grate or shelling screen like this and crack the peanuts open and the peanuts fall through. So just to show you, this is what the shelling rate was measured on a machine like this, the rotary sheller. And this is how we measured the grade factors that I'll use to try to predict that shelling rate from the reciprocating sheller. The data set that we used was a 4-year data set from 2015 to 2018 from the Uniform Peanut Performance Test. 3 locations were included: Marianna, Florida, Stillwater, Oklahoma, and Lewiston, North Carolina. And 26 to 35 genotypes per location year combination were in these data sets. There was no replication on a plot level because the sample size needed for the National Peanut Research Lab to do their shelling work is larger than a single plot would provide. So those individual reps were combined together to provide a sample for the shelling. The cooperating breeders in the USD utilize the USDA grade standards and the reciprocating shellers, as I mentioned. So the NPRL shelling and physical properties evaluation is published, and some of those are on the website, and it's conducted, as I said before, with rotary shellers that mimic commercial applications. Both of these, both the rotary shelling process and the reciprocating shelling process, collect meat, whole, jumbo, mediums, number 1 splits, other kernels, seed weight, and other factors. But the question we have is, do these mimic each other? In other words, do those outturns from the grading process, the shelling process, from the rotary sheller and the reciprocating sheller mimic each other enough that we could use one to predict the other? They also collect other things such as the 16th inch seed pod size distribution and, of course, shelling rate. So the way we began the analysis was a broad correlation to determine potentially related variables. Then we used that information to develop linear regression curves and lines to determine predictive ability of the variables. Then we used most recent seasons on either side of the 2015 and 2018. So we used 2013 and 14 and 2019 as a validation set to determine how predictive these equations were. This is just an example of the shelling rate information from the NPRL. You see here in the top box the initial shelling weight, which I'm going to call the first stage shelling. As you see here, the first stage shelling. They begin with a certain weight of peanuts, and they shell until the peanuts have fallen through those grates. That grate was a 28 in this case, and they calculate the amount of time and weight that was shelled during that time. In this case, 1,426 grams were shelled in the first 129 seconds over the 28 grate. And then we also looked at the total grams shelled per minute overall of the different grate sizes that we see here. And those are the 2 variables that we're going to try to predict: the initial shelling rate and the total shelling rate. This is an example of the variability that's seen among cultivars. You see that as low as around 1,300 to as high as over 2,000 grams per minute on the first stage shelling rates. And we see similar variation with the total shelling rate. And we did do an initial analysis of variance to determine if there was genotypic variability. And indeed, there is genotypic variability in shelling rate capacity both first stage and total shelling rate among the cultivars that we evaluated in the study. So this is the results of the broad correlation analysis. It is truncated some. We don't include every variable here, but just to show you that we had 3 locations, North Carolina, Florida, and Oklahoma, and the number of genotypes from each location over those 3-year periods, and we analyzed over years but by location because of the variation was quite dramatic over locations. And of course we can't replicate over years, but we can replicate in these individual locations. The interesting thing was that there was less predictability, less correlation between these various grade factors and the first stage shelling, especially in the Florida location and the Oklahoma location, but more correlation between those factors and the total shelling. And I've highlighted in blue here all the areas that were most correlated, most consistently correlated across locations with total shelling rate. So first of all, locations differed, and also the first stage shelling rate was highly correlated with each other. So from 0.64 to 0.9, so they are very similar characteristics that we're measuring here. But we're going to focus on 3 of the characteristics that seem to be most consistently correlated. The splits, the jumbos, and the seed count were the most consistently correlated with total shelling rate, and from the rotary sheller. And that was also true from the reciprocating sheller. The jumbos, the splits, and the SMK seed count were most consistently correlated with the shelling rate. So we're going to focus on total shell rate using splits and seed count as regressors, as well as the jumbos. So this is an example of the regression analysis that we did, and this was from Lewiston, North Carolina. The splits from the rotary sheller using splits from the reciprocating sheller to try to predict the total shelling, the first stage shelling rate in this case. And we see that in the case of the rotary sheller, there was quite a good relationship between the splits that were generated and the rate at which the sample shells. It's a negative relationship. So basically, the longer the seed pods were in the sheller, the more splits that were generated. It sort of makes sense that the longer it's in them, the more splits it's going to generate. But that did not hold true on the reciprocating sheller. And as we see in the next slide here, you can tell why. Look at the range of splits that were generated in the rotary sheller. Went from 8 or from low 1% up to 16% on our scale, whereas in the reciprocating sheller, it was only up to less than 4% of the splits generated in the reciprocating sheller. So of course, we don't see the same range, so we're not going to be able to see the same relationship between the reciprocating splits from the reciprocating sheller that we see from the rotary sheller. Then we looked also at the Marianna location, where there was a bit of a correlation between the splits from the reciprocating sheller here and the first stage shelling rate that was seen from the rotary sheller. But the results were not strong. There was definitely a linear relationship, but there was quite a bit of variability around the lines, explaining only about 20 to 25% of the variation in first stage shelling. And you see here that there was a broader range of splits generated in the reciprocating sheller process from Marianna, up to over 20%, about the same range that we see here in the rotary sheller from the same samples. But again, a preponderance of those less than 10%. So certainly the reciprocating sheller just does not generate as many splits in these 2 locations as the rotary sheller does. Now we did the same thing in Oklahoma, and we see a little bit better correlation here, a little bit better relationship, a strong relationship between the splits and first stage shelling rate. But again, only about 35% of the variation explained. But again, if you look at the range of splits generated in the reciprocating sheller in that location, quite a bit more splits generated here, up to 20%, and a bit more evenly spread in this case compared to the rotary sheller in Oklahoma. So basically, it looks like the splits are a good corollary. So we'll do that and look at at those regressions for all these characteristics. And so what we did is a 1-by-1 and multiple regressor process for using total shelling and first stage shelling across all 3 locations, North Carolina, Florida, and Oklahoma. And I have here the F value for regression, as well as the R square that was generated from that for each of the locations, and using splits, jumbos plus splits, jumbos plus seed count, and splits plus seed count. And we also did the three-way, but there was no significant effect of the three-way over the best two-way, so we're not going to show that here. So in summary, you can see that the very best relationships were generated between splits plus seed count. Splits and seed counts used as two different regressors in the model, and they explained about 40 to 45%, up maybe 50% of the variation in total shelling rate, but not in first stage shelling rate you see here. So we decided to focus on this total shelling rate here using these two variables to see what we get and what kind of equation we can develop. And I'm going to focus on Florida. I did not do this just for the other locations, but just for the Florida data. So again, focusing on the Marianna, Florida data, what we see is that the using splits and seed count from the reciprocating sheller to predict the total shelling rate from the rotary sheller, we had a very good relationship here, strong relationship between the variables in regression and the total shelling rate, and pretty good, about 40 to 45% of the variation explained by these two variables. So we wanted to use this equation here that was developed from this model to try to predict other locations in other years. And what we find is this is what the model looks like. So this is that model, and it's the what we're seeing here is a total shelling rate that was observed from the rotary sheller, and that was predicted from the reciprocating sheller. And it's a pretty good relationship, again, explaining about 44% of the variation. But the question we have now is, can we use this equation in future years or previous years in the Florida location that would allow us to predict other seasons? And so we did that looking at the 2019 data, and again, the data that we used to generate this equation was from 2015 to 18. So this 2019 data is not included in the data set that generated the equation that we see here, but it did actually predict the 2019 shelling rate to a fairly good extent, about 50% of the variation explained here with this using this equation. So we wanted to apply that to other seasons. So you see here that in addition to the 2019, which you see here, we also applied it to 2014 and 2013, and we saw that in 1 year, in 2014, there was a good relationship, but not in 2013. So we're not sure why, but there certainly is year-to-year variation. But at least in 2 of the 3 years, we saw at least 40% of the variation explained for the using this equation to explain the variation in total shelling rate of these genotypes. So in summary, total shelling rate and first stage shelling rate are highly correlated, from about 0.64 to 0.91. The seed count and ELK percentage and split percentage were moderately correlated with first stage shelling rates. And so we use those in a regression, and it showed that location specificity is important, that there's a lack of relationship largely due to the small range in splits generated from reciprocating shellers in some locations in some years. Total shelling rate was more predictable than first stage shelling rate, and the two variables seed count and split percentage were the most predictive of total shelling rate. The equation developed using these two variables explained about 40 to 45% of the variation in total shell rate in 2 out of 3 seasons that were not in the regression database. So it appears that prediction of total shelling rate from a rotary sheller using seed count and split percentage from a reciprocating sheller is possible. And thank you for your time and attention. If you have questions about this presentation, I can be reached by email at btillman@ufl.edu. And I also want to extend a thanks to the National Peanut Research Lab for generating the shelling data from the UPPT, and Dr. Kelly Schnell and Tom Islip and Jeff Dunn for their participation as well. Thank you very much.